Now we're going to consider basically the confidence interval formula and where it comes from when we're working with independent samples. Now remember, we start off by having to know what the critical points distribution is when we do some type of estimation problem. And that sort of goes back to what we would use as a test statistic if we were doing a hypothesis test. So really for hypothesis tests, what we're going to do is sort of find the sample mean and the sample standard deviation for each of our two sets of data. And we obviously also will have the sample size. And then what we're going to do is sort of calculate, except we're not really going to do the calculation, this type of arithmetic. So what we're doing is we're going to take the difference in the two sample means minus, in a hypothesis test, we'd tell what we think mu1 minus mu2 is. Now for this course, we actually always say that is equal to 0. So the difference in the two population means basically indicates there's no difference in the two populations in terms of this mean calculation. The denominator is going to be basically how different could y bar 1 minus y bar 2 be if you took lots and lots of samples and repeated this process and plotted y bar 1 minus y bar 2 values. Now remember, when you do the subtraction, you're getting one number, and if you plotted all of those differences, all of those single numbers, this denominator tells you how spread out those differences in the sample means would be. And this thing turns out to have basically a t distribution with degrees of freedom that we're just going to let the computer calculate for us. Now I'm going to show you why we're doing that. Your book says we leave it to the computer or calculator. If you're curious and really want to see the formula, look in the footnote down here at 7. So I'm going to scroll down here and show you this formula. And this is what we would have to do to calculate the degrees of freedom. Okay? Are you sorry you looked? Well, probably so at this point. But we're not going to do this calculation by hand. We're going to let the computer, which is really good at doing number crunching, we're going to let it do it for us. So let's go back to the notes. Now, this is going to be valid when we have both samples, right, one from each population, which are randomly collected, so we've got that randomness, and they have to be independent of each other. Okay, if they're paired in some way, they're not independent, then we wouldn't use these methods. We'd use something else. The populations either need to themselves be normally distributed, right? Each of the two populations from which we're drawing the samples, or we need the sample sizes, right? And we've got one sample size for the first sample and a second sample size for the second one. Both of those would need to be at least 30. And then neither of the population standard deviations, and again we have two of these now, sigma 1 and sigma 2, they have to be unknown. So what we're doing is we're using the sample standard deviations in those formulas. Now the confidence interval formula actually turns out to take the difference in the sample mean, so that was what you called your point estimate, plus or minus a t critical point. And you can actually look this up using table T, as long as the degrees of freedom that StatCrunch gives you end up being in the table. And then you could, verify the calculations for StatCrunch. And then this is your standard error of the difference in sample mean. So that would be the denominator of the test statistic from that previous slide. Now we're going to do all the testing and estimation on the computer using StatCrunch. So we're not going to do this stuff by hand, but what you're going to have to do is read the output and find the test statistics and p-values if you're doing a hypothesis test, or the endpoints, the lower limit and upper limit for confidence intervals. And then, so what we're doing is we're switching away from the arithmetic and we're focusing on what the meaning of the analysis really is. So you're going to have to do one thing on your assignments and stuff, and that is to keep straight what we mean by subscript 1 and subscript 2. You'll notice I had like y bar sub 1, y bar sub 2. You need to identify what is group 1 and what is group 2. And really, it doesn't matter which way you put them in the computer, as long as you make everything match that pattern. So you can either change the subscripts. If you're comparing males and females, you could change 1 to males and 2 to females in all the notation, and then it's clear. Or you could just say 1 is the male group and 2 is the female group. So let's look at this first example. Suppose I want to estimate, so that tells me I'm doing a confidence interval, the difference between men and women for mean diastolic blood pressure. A sample, and we'll assume this is a random sample, of course, of 16 males and 13 females were examined for diastolic blood pressure. So we had 16 males, we measured theirs, diastolic blood pressure, and 13 females, we measured theirs. The data was analyzed in StatCrunch. You may assume diastolic blood pressure readings are normally distributed for each gender. So this tells me the original populations are normally distributed. Calculate and interpret a 99% confidence interval for the difference in mean diastolic blood pressures for men and women. And remember, difference means answer to a subtraction problem. So keep in mind, in all the inference we're doing right here, we are talking about the answer to a subtraction problem. Now, in order to get the analysis, what you would do is in StatCrunch, you'd go to Stat, T-Stats, to Sample, and if you had your individual measurements, right, your 16 and 13 measurements in 2 columns, you'd say with data, and then sample 1, the values would be in, and I would have it in a column called males, and that would go in right here. Sample 2, values in, and I would click this little box here and drop down and select females. Now, it's very important where it has this calculation option that you do not check that box. Okay, make sure it is not checked. If there's a check mark in there, go and click on it so it unchecks the box. What that does is uses a different formula in the calculations. Okay, so we could talk a little bit about whether to check the box or not, but we're just going to assume we're not going to check it for now. Then click the circle by confidence interval, right, because you're wanting to do a confidence interval. If you were doing a hypothesis test, you'd click this box. But we're going to perform a confidence interval. And make sure the level of confidence is set to what you want. And we ask for a 99% confidence interval. And then just click the compute button. Now what comes out is the output on the next slide. So what it'll do is it'll tell you what the level of confidence was. It'll tell you what was group 1, what was group 2, and then it tells you that it's doing a difference between the 2 means. It tells you it used the unpooled or without pooled variances formula. And then this is the output box that you sort of get. So it tells you it's estimating this sample difference. This is like y bar for males minus y bar for females. This is that big square root of s of 1 squared over n1 plus s squared 2 over n2. If you did that calculation, you'd get about 3.301. It calculated the degrees of freedom, okay, and I may have rounded this off or something. Sometimes it's not a whole number, and we just drop off the decimal part and use 24 degrees of freedom, okay. Now the lower limit is negative 2.94 and the upper limit is 15.53. Okay, so what I did here was actually printed out for the males and females the sample sizes and what the 2 sample means are. So these are your 2 y bars and these are your 2 s values. This is the only example I'm going to go through and show you the arithmetic on. Okay, everything else we're just going to let the computer do the number crunching for us. Now remember, StatCrunch gave us this interval, so let's go back and see what we would get if we did the hand calculations. So here's my formula. So what I would do is take the y bar for the first group, male, 77.38, minus the y bar for the second group, 71.08. When you take that difference, you get the 6.3. Add and subtract. Now, where did the t-score come from? 2.797. Well, remember, we were told there were 24 degrees of freedom, so you could go to table T, look in the 99% confidence column, so that's the one on the far right, and if you look for 24 degrees of freedom road, that last column, you'd get a t-score of 2.797. Now the other part is the square root of 8.35 squared over 16 plus 9.22 squared over 13. So I'm just filling the values in right here over here. And when you do all that calculation, you get 9.2 and some other numbers. Okay, so when you do 6.3 minus that, you get negative 2.93 when you round off. And when you, when you add, you're going to get 15.53. Give you a minute to look at that. Now, the only difference is that we got a 3 right here, whereas StatCrunch got a 4. Now, what StatCrunch would do is it would keep more than 2 digits after the decimal point for the means and standard deviations. So what it's doing is a calculation that probably is a little bit more accurate. So we probably have a little bit of round off error, which is why this first number is different with a 3 and a 4 in the hundredths digit from the hand calculation. But the upper end point is the same for both. Now what we want to do is think about, okay, what does this interval mean? Okay, and remember, this interval is giving me the answer to a subtraction problem. It's critical that you keep that in mind. Okay, so we're going to use StatCrunch's interval of negative 2.94 to positive 15.53. Now the negative 2.94 tells me that the thing I'm estimating, which is what? The mean diastolic blood pressure for males minus the mean diastolic blood pressure for females. The answer to that subtraction could be negative 2.94. Well, when you have two numbers and are subtracting them and you get a negative, that tells you the second number is bigger by the magnitude, ignoring the negative part, value. For example, 6 minus 8 is negative 2, tells me that 8 is 2 units bigger than 6. Okay, so since this difference is negative 2.94, the mu for females could be 2.94, and the units would be millimeters of mercury, more than mu for males. So that's this extreme. Now it could be all the way over here at this positive number. Well, positive 15.53 tells me that that difference in the two population means could be 15.53. Well, what would that mean? Well, when you do a subtraction and get a positive number, that's like 7 minus 4 is positive 3, because 7, the first number, is 3 units bigger than 4, the second number. So what this means is that mu for males could be 15.53 millimeters of mercury bigger than mu for females, the second value. And really, it could be anything in between those two extremes. And basically, it could even be 0. Now, if two numbers subtracted give you 0, what does that tell you about the two numbers? Hopefully you understand that when you take the difference between two numbers and get 0, it means you've got the same value in the two spots, like 5 minus 5 is 0. So basically we go from females having a larger mean to it could be equal, right? The two means could be equal if you're looking at the 0 point, all the way up to the males being larger, which means I really don't have a definitive answer. So your interpretation is going to basically have 3 components. It's unclear at the 99% level of confidence whether males or females have a higher mean diastolic blood pressure. if, and then pick one of the groups, if males have a higher mean diastolic blood pressure than females, it is by no more than 15.53 millimeters of mercury. If, on the other hand, females have a higher mean diastolic blood pressure, I estimate it's by no more than 2.94 millimeters of mercury. Let's look at the interpretation in a generic sense on the next slide. So in that example, the interval went from a negative number, it included 0, and then went to a positive number. If the difference in the two numbers is negative, it tells you the second one is bigger. If the difference is 0, they could be the same. And if the difference is positive, the first one is bigger. So anytime you have an interval that goes from negative to positive, and that is the difference or the answer to a subtraction between the two numbers, you're going to have basically three sentences. Number one, at the specified level of confidence, it's unclear which group has the larger population mean. If the first mean is larger, it's by no more than, and remember, if the first number is larger than the second, first minus second will be positive. So really, the magnitude of the positive number goes in that blank there. If the second mean is larger, it's by no more than, and then you give the other number. And don't put the negative sign in there, because you're already saying the second one is bigger. You just want to say by how much at that point. Okay, so what would a solution really look like once we've sort of understood the confidence interval, we've sort of muddled through what all the interpretation means? What am I going to be looking for in terms of a complete solution? Well, how do you work confidence interval questions? Well, you want to start by defining what it is in terms of the parameters that you're trying to estimate. Then you would give your formula that you would use to calculate the interval, and then sort of plug the numbers in and calculate it. Now in this case, you're just going to read it off of StatCrunch. Then you want to interpret the interval, right? What do those numbers tell you about what you're trying to estimate? And then finally, if you're asked, be able to verify that the method is valid. So what would our solution look like going through those steps? Well, first we want to define the parameters, right? So mu sub male minus mu sub female represents the difference between the mean diastolic blood pressure for, and now I want to generalize, right? All men, the population of men, and the mean diastolic blood pressure for, again, generalized, all females, okay? So remember, mu represents the mean for the entire population, not just the ones in the sample. 2 and 3 we sort of stick together. Give the formula used to calculate the interval and then do the calculation. So that just means read it off of StatCrunch. So I put down the formula. I define that 1 represents the male group, 2 represents the female group, and then here's my interval. What I would want to do following is then go back and interpret this interval, and that's where you've got to spend a little bit of time thinking about, okay, so if I do male minus female, I'm estimating the mean for all of them, and I could get a negative or a 0 or a positive. What does all that mean? Okay, so then you would come up with your interpretation, right? So it's unclear at the 99% level of confidence whether males or females have the higher mean diastolic blood pressure. If males have a higher mean diastolic blood pressure than females, it's by no more than 15.53 millimeters of mercury. If, on the other hand, females have a higher mean diastolic blood pressure, it's by no more than 2.94 millimeters of mercury. And then last, we would go through the validity check, right? Is it valid? A random sample of males and another independently collected random sample of females were measured for their diastolic blood pressure. So we have the independent random samples. Each population of blood pressure measurements we were told to assume that they were normally distributed. Okay, so we were told that, so the populations themselves are normal, so the sample sizes don't matter. And then we didn't have sigma for males nor sigma for females. Okay, so neither population standard deviation was known, so we ended up using the sample standard deviations in the calculations. So the method is valid, and those are the reasons why. So this is the first example of a confidence interval for the difference in two population means, assuming your data is collected using independent samples.